So we're going to move on to the fourth speaker now, Dr. Michael Hall from the University of Newcastle. He is a senior lecturer at Newcastle University and has a background in synthetic, organic and natural chemistry. And he's going to talk to us today on high-throughput nanoscale crystallization of bioactive natural products for X-ray crystallography.
So thank you, Matthew, for that introduction and for the opportunity to be here to talk to you today. What I'm going to talk to you is a little bit different to maybe a number of the talks in the sessions. We're really taking a much more of a chemistry direction on looking at some natural products, particularly for antibiotics, rather than a lot more of the biological talks. But hopefully the stuff we're going to talk about is going to underpin some of the work that other people are doing. Well, what I'm going to talk about is really some nanoscale crystallization of natural products for then X-ray crystallography analysis using a technique called encapsulated nanocrystallization, or ENACT. A lot of the preliminary data that I'm going to talk about today is being published now in this paper in Chem earlier this year. So feel free to go and have a look there if you want to see some more, or drop us a line. So why am I going to talk about growing crystals of molecules? Really, that comes down to this kind of problem. So this was a project that we did some years ago, and this is probably very typical of what a lot of people are doing when they're in the natural product discovery field. Is they'll find an interesting bacteria. Here's a Streptomyces. You're then going to do some level of fermentation work in order to grow some, and then you're going to try to work out what the interesting bioactive might be in that whole process. Obviously, to do the structural identification of the molecule, what you're going to need is do a lot of work. So people have talked about genomic methods for looking at molecules, and that's fine if the genome is either known, the biosynthetic cluster is known. So genomics is great for identifying known molecules. It's not so good for unknowns. Or if you're in a well-conserved type natural product like a polypeptide, again, the genomics can help you a lot. Alternatively, you get into things like LCMS and dereplication through these methods. NMR is incredibly important, but obviously you need reasonable amounts of material. But of course, the gold standard for getting structural data on a molecule is really single crystal X-ray diffraction. That gives you all your connectivity. It gives works out all your formula, all your atoms, and even it can work out absolute stereochemistry for you. So then the problem you often have is you have a few milligrams of natural product. You really need to grow a nice crystal of it to do the X-ray crystallography. And if you could do that, of course, then we can do the diffraction analysis. We can work out the structure of our molecule. And as I say, that gives you structural information and stereochemical information as well. But how do we do this with such small quantities? So typical crystallizations in chemistry are done on milligrams at a time. They might take several weeks in order to conclude. And if you only have 5 mg of natural product, that's probably going to be a year's worth of crystallization experiments before you get anywhere. So what we've been doing is working out some methods to do this sort of nanoscale crystallization of organic molecules, of molecules that really dissolve in organic solvents, and this includes all sorts of natural products. And we took some inspirations from protein crystallizations of using sort of under oil type techniques. So what we actually do is we take a little droplet of oil on a 96-well plate, we inject into it a solution containing the sample of our natural product or other organic molecule. Then we seal the plates and we let this over time concentrate until we get to a supersaturation point and then some crystal growth. And to do this, we can use these robotics from STP Lab Tech, really designed for doing protein crystallography. And we're operating on a very small scale. So we're using a few hundred nanoliters of oil, 50 nanoliters or so of sample. So that means for every crystallization experiment, we're typically using a couple of micrograms of material. So obviously, if you're very limited in terms of the amount of natural product you might have, being able to do a few micrograms per experiment is very useful. Does that work? Well, let's have a look at an example at the top. So here we can see a droplet of oil containing our sample. Each of these droplets is maybe a millimeter or so across. It's 250 nanoliters. Over time, these concentrate and we see crystal growth. Down the bottom here, this is a demonstration experiment using this red colored dye, and hopefully you spotted the nucleation occurring in the bottom corner of this well, and then crystal growth this was actually over a few days under the microscope. And we can do we use these glass 96 well plates such as this. We can run lots of experiments at the same time, and then hopefully we get lots of nice crystallization outcomes. So can we use that to get structural information? Because you often worry the crystals aren't going to be big enough for X-ray. Actually, yes, it works fine. And these are some of the compounds that we've published. This is really a mixture of simple organic molecules. But hidden amongst this, you might spot cholesterol in the middle as a nice example of a natural product. And vitamin B12, which we had in there as a rather nice kind of example of quite a complex natural product architecture. But we originally designed this work to look at not only natural products, but also small organics and any real sample limited organic molecule. And what we've been doing now is trying to optimize some of this for really doing natural products where we have very little material. So currently, the students in the lab have been working on a protocol where we start with 5 up to 10 milligrams of material. We can go a little bit lower than 5 if we need to. And from there, typically we make up around about 12 or so solutions, each containing about 1 milligram or so, or half a milligram or even less of sample. This is quite a large vial. Actually, these are normally in a few microliters of solvent. And from here, we set up a kind of first generation experiment where we'll run 39612 plates. We'll do about 300 experiments out of about 12 different solvents. And then we look for crystal formation. And typically either we see good crystals at that stage, or we'll see indications of good conditions. So when we can do sort of optimization experiments, so we can go to second generation methods, where we then again will run more plates, we'll run more experiments. We can have other solvents or mixed solvent systems. And these are often designed based around what we're seeing off this initial solvent screen. And again, after 2 weeks, we normally get readouts. So again, we're looking for crystals of this nature. And I should point out these crystals are a few tens of microns kind of in each dimension. And this is some example of actually a natural product crystallizing out from one of these kind of extremes. So from a few milligrams of material, we actually can get hundreds of crystallization experiments, really maximizing the chance of a good crystal. So I should say that with some working with some collaborators, we have been working on unknown natural products, and I think in the last few months we've solved about 6 new natural product structures. We can't share them with you at this stage, so I'll share with you some commercial materials, some natural products and natural product derivatives that you're probably all quite aware of. So we also, in order to set up some of these protocols, we looked at commercially available natural products. Here's spectinomycin, an antibiotic, which is clinically used, and using our approach. So this, again, just with 3 plates and a few milligrams of material, we could grow very good quality crystals. This is actually the HCl hydrate of spectinomycin, actually an unknown crystal structure at the moment, well, until we publish it. And I'll just note the FLAC parameters here. So this is just telling us that we're getting absolute stereochemistry from this crystal structure as well. So from this little crystal that we're growing in one of these droplets, a few tens of microns across, we can get very good data. Just to give you a nice antibiotic example, rivampicin, which of course is a semi-synthetic natural product. Again, we looked at similar kind of experiments, and again, we've grown some nice crystals of this. This one on the right it's actually got 3 molecules of rivampin and 2 molecules of 1,4-dioxane in the crystal structure. So it's a new crystal structure, actually, of the rivampicin molecule. And really, they're just some examples of showing you how we can look at natural products. So just to summarize, really, we've been working on this solution phase nanoscale crystallization type approach, which really applies to any organic molecules, but we've got a particular interest in natural product structural elucidation. We can control lots of variables on the robots in order to try to maximize the experimental space that we look at. And our current work is doing this. We're taking approximately 5 milligrams or slightly more of a natural product. From there, we can get anything up to 900,000 or so experiments done. And normally that's enough for us to find a good crystal that we can then go forward and do X-ray crystallography So I'll just finish by thanking all the various people involved. So Ronnie, Andrew, Locke and Lena have done a lot of the preliminary work on this. Paul is our robot contact from STP Lab Tech. Charlie and Mike are doing a lot of the crystallography. Sarah doing statistical analysis on our results to help us be a little bit predictive in terms of crystallization. And currently the project is being run by Jake and Tom, who are looking at various aspects of it. And that's me done. And just to thank the organizers and you again for your attention, and I'm happy to answer any questions.
Brilliant. Thank you very much, Michael. Fascinating talk there.